Hi class, in this video we will take the wave-like nature of matter and connect it to atomic structure. And what we learn here in this video about atomic structure is actually what holds true today. So until something better comes along, this is the best we've got. After French physicist Louis de Broglie discovered the wave-like properties of an electron, mathematicians such as Schrödinger came along and was able to describe the wave-like behavior of an electron mathematically. And we know this as the Schrödinger equation. And this is what started the field of quantum mechanics. We're going to just skim the surface of quantum mechanics in this course and just have a basic understanding of what we need to know to understand the structure of an atom. At first glance, the Schrödinger equation looks quite simple. However, this H value, the Hamiltonian operator is what it's called, has a number of mathematical terms within it. And so it does take quite a bit of calculus to solve this equation. If we do solve the Schrödinger equation, we get a series of wave functions denoted by the Greek letter psi. Psi1, psi2, psi3, for example. Each solution to the Schrödinger equation corresponds to an allowed energy level for an electron. This fact that electrons can only exist at certain energies highlights again the fact that energy is quantized. We can only have this stair-step of energy that corresponds to these different energy levels. No electron can have an energy in between these different steps. However, this psi is not going to be super useful for us. It turns out that psi squared, the square of the wave function, is going to be more useful for us. It describes the probability of finding an electron within a certain three-dimensional space. And this three-dimensional space is what we call an orbital. So what exactly is an orbital? Well, an orbital is just what I said, a three-dimensional region of space that can be occupied by an electron. We have to be careful with how we interpret that statement. We know that electrons not only have the particle-like behavior, but also wave-like behavior. So we have to come up with a mental image that captures both the particle-like and wave-like nature of an electron. It's not simple as visualizing a particle bouncing around in a certain three-dimensional space. So, if we take an orbital and think of it as a cloud, similar to that of a cloud in the sky. Now let's compare an electron cloud to a cloud we might see in the sky. There are probably more differences between electron clouds or orbitals and clouds in the sky, but if we focus on those differences, we can have a better mental picture of exactly what an orbital is. First, clouds in the sky can come in all different shapes and sizes. However, electron clouds or orbitals come in only a certain number of defined shapes and sizes. We'll look at those more in the next video. Second, a cloud in the sky is composed of billions of individual water molecules. However, an orbital or electron cloud is a single entity, although it can be thicker or thinner in some areas. And lastly, a cloud in the sky has defined edges. It is possible to define a region of space that contains 100% of the cloud. However, when we look at an electron cloud or an orbital, it is not possible to define an end. We use the term electron density, which is associated with the probability of finding an electron in a region of space. And the electron density is going to be much higher around the nucleus, where that attractive force is the greatest, and it will taper off as we get farther and farther from the nucleus. However, it actually never ends. The shapes of the orbitals and the figures that you'll see define the region of space that you will find 90 to 95% of that electron density. The remaining 5 to 10% of the electron density tapers off as we get farther and farther from the nucleus. But if we want to define a space that contains 100% of the electron density, we must include the entire universe. So in summary, an orbital is a region of space that can be occupied by electron density. That idea will encompass both the wave-like and particle-like nature of an electron. Thanks for watching.